For decades, every astronomy textbook told us the same thing. At the center of the Milky Way sits a supermassive black hole called Sagittarius A, 4.3 million times the mass of our Sun, compressed into a region so dense that not even light can escape. In 2022, the Event Horizon Telescope gave us an image, a glowing orange ring bent by extreme gravity, a dark shadow at the center. Case closed. But in February 2026, a team of physicists published a paper that asked something no one expected. What if that shadow is an illusion? What if the object anchoring our galaxy is not a black hole at all, but something far stranger? We have known something massive lives at the galactic center since the 1930s. But the real proof came from two teams, Reinhard Genzel at the Max Planck Institute and Andrea Ghez at UCLA, who spent 30 years tracking individual stars orbiting an apparently empty patch of space. The closest star, S2, swings around Esquire-Fartro once every 16 years, reaching 7,650 kilometers per second at its closest approach. That is 2.5% the speed of light. The only explanation is an object of 4.3 million solar masses packed into a sphere no wider than 25 million kilometers, small enough to fit inside the orbit of Venus. In 2020, Genzel and Ghez shared the Nobel Prize for proving this compact object exists. But the Nobel Committee used those words deliberately, compact object, not black hole, because nobody has ever directly proven what it actually is. And there is a deeper problem. The James Webb Space Telescope has found enormous compact objects in galaxies less than 1 billion years after the Big Bang, objects that appear to contain black holes of hundreds of millions of solar masses. That is simply not enough time for the standard formation model to work. Something else must be happening. This is where dark matter enters the story. Dark matter makes up 85% of all matter in the universe. We know it exists because galaxies rotate too fast for their visible mass, and galaxy clusters bend light in ways that demand far more mass than we can see. But we have never detected a dark matter particle. In February 2026, a team at the Institute of Astrophysics La Plata in Buenos Aires proposed a radical alternative. What if dark matter is made of fermions? And what if Sagittarius A is not a black hole, but a dense, stable core of this fermionic dark matter? To understand how this works, you need to know one rule of quantum physics called the Pauli exclusion principle. No two identical fermions can occupy the exact same quantum state at the same time. Imagine a parking lot where every space is unique. Once the ground level is full, new cars are forced upward. Fermions do the same. They refuse to share the same quantum parking spot. When gravity tries to crush them together, they push back. That resistance is called quantum degeneracy pressure, and it is what keeps white dwarf stars and neutron stars from collapsing. If dark matter is fermionic, it would do the same. Instead of collapsing into a singularity and forming an event horizon, it would create an ultra-dense, stable core supported entirely by quantum pressure. And from the outside, it would look almost identical to a supermassive black hole. The La Plata team compared their dark fermion core model to the actual observational data, the orbit of S2, the motion of 5 mysterious G objects stretching and deforming under Esquire-A's gravity. The result stopped me cold. The dark matter core reproduced those orbits with less than 1% difference from the black hole model. Current data literally cannot tell them apart, but the model does more than match orbital data. In 2022, the European Space Agency's Gaia mission revealed that the outer arms of our galaxy slow down more sharply than most dark matter models predict. Fermionic dark matter naturally produces exactly this sharp drop-off. Then, in 2024, a team led by Carlos Arguelles demonstrated that a sufficiently compact dark Fermion core can produce an event horizon telescope image almost indistinguishable from a black hole. No event horizon required, no singularity needed, just enough mass packed into a small enough space to curve space-time to the breaking point. Drop a heavy glass sphere in front of a candle. From any angle, the light bends around it, creating a ring. You never see the sphere itself, only the distorted light. That is the cosmic illusion at the center of our galaxy, and here is where it escalates. If Sagittarius A is a dark Fermion core, then dark matter is not a diffuse, passive cloud drifting through the cosmos. It is a substance that can collapse into dense, invisible objects. The supermassive black holes we have catalogued by the thousands may not all be black holes. It would also explain the James Webb Space Telescope's puzzling early universe objects. Dark Fermion cores can form directly from collapsing dark matter halos, without stars, without billions of years of mergers. The timeline problem vanishes. So how do we settle this? The answer is photon rings. Around a true black hole, space-time is curved so extremely that some particles of light can orbit the black hole before escaping. They trace out thin, luminous rings nested inside the bright ring we already see, a direct signature of an event horizon geometry. Drop a marble into a funnel. It spirals in. Now imagine a marble that circles the rim forever, never falling in. Photon rings are light trapped in that eternal spiral, skimming the edge of oblivion. If we detect photon rings around Sagittarius A, the case for a black hole becomes nearly airtight. If we look with better instruments and find nothing, no photon rings, no subrings, then physicists will have to take the dark Fermion core seriously. Missions like the Black Hole Explorer, designed to put radio observatories in space linked with ground telescopes, could make this measurement within the next decade. For now, the honest answer is that SGR-A is still best explained as a supermassive black hole. The dark Fermion core remains a bold hypothesis, not a replacement. But when a team of serious physicists can publish a paper showing that current data cannot distinguish between a black hole and a dark matter core, it means the center of our galaxy is not a settled question. It is an open one, and the answer, when it comes, may tell us what 85% of the matter in the universe actually is. We are 27,000 light-years from the answer, but every year we get closer. Subscribe and be there when the next image arrives.